Dear students, I am Dr. Rukmini from the Department of Electronics and Communications Engineering, Vignan University. I am going to take the course Electronic Devices and Circuits, and which is a very fundamental subject for the subsequent semesters also. Now, let us see. Before going to the details of this subject, let us see what is meant by electronics. See, here it is nothing but the study of how to control the flow of electrons. All of you know that the flow of electrons is nothing but current. Then where this situation comes? Where this control flow of electrons can be seen? Let us see in case of televisions, DVD players, laptops, desktop computers, mobile phones, iPads, iPods, ovens, washing machines, game consoles, printers and radios. In all these things, we need to control the flow of electrons. It is nothing but, if you take television, you have to control the volume or picture contrast, brightness, etc. So like that, in all these electronic applications, you have to control the flow of electrons. Now let us see what you are going to understand, or the main objective of this electronic devices and circuits is, first thing is you will understand the fundamental concepts of semiconductor devices, because the control flow of electrons is possible only with the help of semiconductor devices. So we are going to understand the fundamental concepts of semiconductor devices such as a junction diode, transistor, an advanced version of the transistor, MOSFET, etc. and the corresponding design circuits for specific application. The second objective of this particular course is, this is the basic fundamental subject for your subsequent semester. So you should get all the fundamentals of this EDC. Next, what are the outcomes after completion of this subject? We are able to understand and apply the usage of semiconductor devices concepts in circuit making, because this is the only fundamental subject for designing any type of analog circuits. Then you can analyze the characteristics and applications of semiconductor diode, BJT and MOSFET devices. And then you can also study various types of feedback amplifiers which are very much useful in industrial applications. Then finally, the experiment and demonstrate the application of analog electronic circuits using electronic components. So these are the total outcomes after completion of this EDC you will come to know. Then the total course is organized into 5 major units. The first one is PN junction diode. Next one is application. After constructing and studying the characteristics, analyzation, then you can find what are the applications of diodes, like diode can be used as a rectifier, diode can be used as a switch, it can be used in clipping and clamping circuits, etc. After that, the extended version of this PN junction diode, this is a BJT, bipolar junction transistor, and the advanced version of this BJT is a MOSFET. We are going to study all the fundamentals of these 3-terminal devices, whereas a PN junction diode is a 2-terminal device. After that, in the 4th unit, we will study how to give the connections to a particular BJT or MOSFET for a proper application. For example, if you want to use it as an amplifier, connections are different. If you want to use this as for a particular switch, connections are different. So all these things you are going to study in transistor biasing. It's nothing but giving the supply. The last one is again the applications of a BJT as an amplifier, and the most specific applications of BJT is as a feedback amplifiers. Let us concentrate on the first unit, which is the PN junction diode. Here the total unit is organized into some specific important points like formation of a PN junction, because we discussed that semiconductors plays a very important role in the flow of electronics control. Therefore, here the major element is a PN junction diode, and so here we will study how to make this PN junction diode. Then operation of a PN junction diode. Then after that we will study the VI characteristics of PN junction diode. Then the diode as a resistor and diode as a capacitor, because physical resistance, physical capacitance are already existing, but here you can use this diode as a resistor and as a capacitor. So these are the two important passive element properties for the diode that we are going to study very clearly. Then some special diodes. So by using these semiconductor concepts, we can design two terminal devices. One is a Zener diode, which has a very excellent application as a voltage regulator, and a tunnel diode, which has been used as a microwave oscillator or a fast operating switch, and a battery diode, which is specially useful in communication systems for tuning purpose. So like that, we are going to, after studying the total concepts from this PN junction diode, you will design 3 new semiconductor diodes which are specifically useful for some applications. Now, before going to the study of semiconductors, where these semiconductors are taken from? So these are they belong to a classification of a material. So that is how the materials are classified. So there are many classification mechanisms are there, but here we will classify the materials in 2 types. The first one is based on the ability of conduction, or you can also say that based on electrical conduction. Another one is based on the energy band diagram. So like this you can classify the materials. So now let us concentrate on based on the electrical conductivity. You know very well that electrical conductivity means how effectively the electrons will flow. Now let us study the first one based on the electrical conduction. That is, first one is the materials are classified into 3 types: conductors, insulators, and then semiconductors. So here we are going to distinguish between these 3 varieties of materials in terms of ability of conduction. See here, first let us take conductors, and here the conductors has a high electrical conductivity. That means a huge volumes of electrons will flow that will constitute a very big current. Almost all the metals behaves as conductors. So few examples are here: silver, copper, aluminium, tungsten, etc. Few more metals are also there. They are best or good conductors of electricity. Then the conductivity is greater than 10 power. So these are the typical values. So how much value of electrical conductivity can be expected usually in the metals? And the most important one is for superconductors, the value of electrical conductivity is infinite. One more important point we have to study here, that is known as the temperature dependence. That means if any metal is heated or any temperature difference is created, what is the effect on that metal? So as soon as the temperature increases, the conductivity decreases. Why? Because the metal will, whenever there is a temperature increment, automatically they will undergo certain type of collisions among the carriers so that the conductivity decreases. So what is the conclusion of this one? In case of conductors, the electrical conductivity is very high, number 1. Number 2, and they have a greater value of conductivity, electrical conductivity. It is represented by the symbol sigma. Then third one is examples. What are the common metals used for getting high electrical conductivity? Number 4, the dependence of temperature. Now let us see what is the variation of electrical conductivity in case of insulators. It is an exactly opposite property of the conductors. So here in this case the insulators has a least electrical conductivity, least or poor electrical conductivity. Examples are diamond, glass, ceramic, mica, plastic, wood, paper, etc. All these are not the good conductors of electricity. Now here, if you see, the diamond has a huge value, 10 to the power of minus 14 Siemens per centimeter. So it's a very poor electrical conductivity material. Then the most important point is its temperature dependence. Usually insulator means it does not allow any flow of current, but as soon as the temperature increases, the conductivity starts increasing. But it's very difficult task to allow insulator as a conductor. Now let us see the third one. Third one is the semiconductors. Its a property lies between conductors and insulators. So that's why we can say that the materials that have electrical conductivity in between conductors and insulators. So that's why why we prefer semiconductors in all electronic applications, or why semiconductors are more important in the electronic field is the control flow is possible. That is, from conductors to insulators or from insulators to conductors, you can vary the behavior so that the control flow of electrons is possible with the semiconductor devices. The best examples, there are so many semiconductor devices, but the successful semiconductor devices are silicon and germanium. Then, what is its temperature dependence? As we studied already in the previous two materials, as the temperature increases, the conductivity also increases. So, only because of this reason only, we are allowing the semiconductors into conducting behavior. So, this is about how the materials are classified based on electrical conductivity. There is another group. This is based on energy band diagram. Already you know the structure of an atom. What is the structure of the atom? For example, if you see the central part is a nucleus, surrounding that there are orbits, and the outermost orbit is consisting of some valence electrons, that is which is an unfilled orbit. So here, for example, if there are 4 electrons in the outermost orbit, this particular outermost orbit, this is known as a valence band. So that can be assumed here as valence band. So now see how the materials are classified based on these bands. See how the materials are classified based on the second method. That is, the materials are classified based on energy band diagram. Okay, so here if you see where this see the structure of energy bands. What are these bands? Valence band, conduction band, forbidden band. So here the valence band is a part of the atom. Suppose if you see the structure of an atom, the central part is known as the nucleus, and surrounding that there are orbits. And the outermost orbit, which consists of the electrons, they are known as valence electrons, which are main source of electric current. So here the electrons associated with this particular orbit, this is known as a valence band. Now, if you want to remove an electron to the other side to constitute any electric current, this other side, which is away from the atom, this is known as a conduction band. So here you are moving the electrons from valence band to conduction band. So in between there is a gap that is known as energy gap or forbidden gap. Forbidden means which does not allow the staying of electrons in this particular area. Therefore, here suppose if you see insulators. In case of insulators, what is our understanding? Insulators, it does not allow any flow of current. That we know already. Why? Because in case of energy band diagram, the gap is very big. That is, from valence band to conduction band, the electrons cannot travel directly to the conduction band because of this big energy gap. So, the energy gap is so wide, that's why no electron can jump into that conduction band. Therefore, here the energy band gap is very large. That's why conduction is poor. And in other words also we can say that in case of insulators, the valence band is full and conduction band is empty. So this is the occupancy of the electrons in the conduction band. Now let us see the complete opposite behavior, that is conductors. In case of conductors, there is no gap in between valence band and conduction band. If you see here, the electron will directly enter into directly removed from the outermost orbit. So almost all metals exhibit zero forbidden gap. So there is no gap. So here you can say that the occupancy of the electrons is the conduction band is full and the valence band may be empty, because almost all the electrons will jump into the conduction band. Next, the property which is between conductors and insulators is semiconductors. Here the gap is very less. See here, the gap is very less. That's why at room temperature, normal temperature, no electron will jump into the conduction band. So we can say the occupancy, it has a partially filled valence band and partially filled conduction band. Suppose if you heat this material or if you create any temperature here, that is in the outermost orbit, if you create any temperature, directly electrons will jump because the gap is very less here. Therefore, the energy band gap is very less. So that's why, based on energy band diagram, we can classify according to the energy gap between the valence band and the conduction band. For example, what is the band gap that we can discuss now? For example, if you see here in case of the germanium, the band gap is 0.78 electron volts, and for silicon, the band gap is 1.21 electron volts. So that's why we prefer semiconductor devices is because of this very less energy gap. Now, let us focus on the semiconductors. So, the semiconductors are classified into pure semiconductors and impure semiconductors. That means what is meant by pure? Pure means the naturally available semiconductor. So, that is known as intrinsic semiconductor. So, the best examples are germanium as well as silicon. So, why we call them as pure means the naturally available intrinsic semiconductors. Now, why we are going for second type, extrinsic, that is extra plus intrinsic semiconductor? The reason is here, the naturally available intrinsic semiconductor behaves as insulator. That is, it does not have any conducting properties. So, just to increase the conductivity, we are adding certain extra materials like extra dopings or dopants, impurities. Why you are calling them as impurity? We declare here as a pure. So, to this pure semiconductor, if you add any impurities, that will become extrinsic semiconductor. Why you are adding dopants? To increase the conductivity. How you are increasing the conductivity? Either by increasing the positive charges, P, or either by increasing the negative charge carrier. So, that's why the extrinsic semiconductor is again divided into P type and N type semiconductor. So that's why there are two types of semiconductors, intrinsic, which is a pure form of semiconductor, which behaves as an insulator, and extrinsic semiconductor, here the conductivity can be improved. So there are P type and N type semiconductor. Now, before going to making of a P type and N type semiconductor, let us study the structure of a silicon, intrinsic semiconductor. The naturally available silicon consists of 4 electrons. Silicon atomic number is 14. So if you write the electronic configuration, outermost electrons are 4. That is, see, this is 1, 2, 3, 4. All these 4 electrons form a perfect covalent bond with the adjacent silicon atoms. That's why they are fixed, so that you cannot allow them for conduction because there are no free electrons. So that's why from this structure we can conclude that in case of intrinsic semiconductor, the conductivity is poor because there are no free electrons for electrical conduction. But in the previous slide, we declared that if you increase the temperature, conductivity can be increased. How it is possible? If you create any temperature difference, the covalent bonds will break. After the classification, now let us see the more details of what is intrinsic semiconductor. It is nothing but the purest form of semiconductor. It's nothing but the naturally available semiconductor. So pure means not the pure, the naturally available semiconductor. And after that, they have perfect insulator. The naturally available intrinsic semiconductor behaves as an insulator. Okay. So next, in order to increase the conductivity, we will apply the process. That process is known as doping. That is, to this pure semiconductor, certain impurities known as dopants are added to increase their conductivity. So that's why we came to extrinsic semiconductor. Therefore, there are two types of extrinsic semiconductors. One is N type, another one is P type. N type means more number of negative charges. P type means more number of positive charges we are creating, so that we are applying for control flow of electrons. Then, how to make N-type and P-type semiconductors? So, it's nothing but making of extrinsic semiconductors. Suppose if you take preparation of N-type semiconductor. N-type means more number of electrons are required for conduction. The examples are arsenic, antimony, phosphorus. The common property among all these is they have 5 electrons in their outermost orbit. Silicon atomic number is 14. It's if you write electronic configuration, the outermost electrons are 4. And if you take germanium, its atomic number is 32 and the outermost electrons are 4. So, in silicon, the total number of electrons are 4. and in germanium the outermost electrons are 4. So to these 4 electrons we are adding certain impurities whose outermost electrons are 5. Let us take phosphorus here. Phosphorus consists of 5 electrons in their outermost orbit. Out of 5, 4 form covalent bond to the adjacent silicon, 1 electron is left. So this electron is known as a electron, or you can call this as a free electron. Now this is the only electron which is responsible for constitution of electronic current. So if you take more number of phosphorus atoms, it will cause a more number of free electrons. So like that we can prepare N-type semiconductor. Now let us move to preparation of P-type semiconductor. For this, you have to select the atoms which consists of 3 electrons in their outermost orbit. We can also call this as trivalent atoms. So examples are indium, gallium, aluminium, boron. Now we have taken boron. It consists of 3 electrons in their outermost orbit. See here, the 3 electrons, they form covalent bond with adjacent silicon, and one place is left vacant. So that is known as a hole, and it is also known as acceptor because it always try to take 1 electron to make a covalent bond with adjacent silicon. So as a whole, we can conclude that for making N-type semiconductor, you have to choose the dopants in such a way that they should consist of 5 electrons in their outermost orbit. Whereas to prepare P-type material, you have to select the dopants which have 3 electrons in their outermost orbit. Now the P material and N material are now ready. So this is P-type semiconductor and this is N-type semiconductor. Okay, now again we have to recheck what is the progress in the energy band diagram after preparing N-type and P-type semiconductors. And as you know already, for intrinsic semiconductor, the energy gap is very small. For example, if you take germanium, 0.78 electron volts. So only because of this gap only, the conduction is poor. So that's the behavior of intrinsic semiconductor. So after modifying this with some extra dopants, the band gap is reduced so that the donor level is observed here. So that's why in case of N-type semiconductor, there are more number of electrons are available for conduction. Similarly, in case of P-type semiconductor, P-type extrinsic semiconductor, the acceptor level is there so that the conduction levels can be improved. Then finally, after making P-type and N-type semiconductor, we can come to one broad conclusion that in case of P-type material, the 3 important parameters are there. The first one is the hole, which is a main source of P-type semiconductor where we created holes. Then another one is somewhere we will have some electrons that are minority charge carriers. So we can say that the holes are majority charge carriers, the electrons are minority charge carriers, and some more atoms are also there. They are known as ions. Ions have 2 specific properties. Number 1, they are immobile. They will not move. They will be stationary. And the second property is they exhibit strong electric field intensity. Therefore, in case of P-type, the important charge carriers are the holes as majority charge carriers. These are majority charge carriers. Electrons are minority charge carriers and ions. Similarly, we can move to N-type semiconductor. In case of N-type semiconductor, the majority charge carriers are electrons. So here, the electrons are majority charge carriers and somewhere there are holes. So they are minority charge carriers and other one is oppositely charged ions, positive ions. Therefore, now P material is ready and N material is ready. Now we are going to make a P-N junction diode. Therefore, if you combine these 2 materials, now it will become a P-N junction diode, which is a main source of control flow of electrons. So how this P-N junction will be formed, that we will see in our next class. Now, after completion of this total unit, let us conclude with 4 assignments courses that you have to answer. The first one is what are the typical values of electrical conductivities, because already we classified the materials into 2 broad categories. electrical conductivity, another one is based on the energy band diagram. So here you have to consider few conductors and semiconductors. Already we discussed one or two examples only. Now you have to take as many as number of conductors, take the examples and give their electrical conductivities. The next one is what is the forbidden energy gap of few insulators and semiconductors. Energy band gap of conductors is not necessary because the energy gap is zero in that case. So select any few insulators like a diamond or mica, ceramic, paper, rubber, and you for these materials you have to give forbidden energy gap values and select some more semiconductors. Also already we declared silicon and germanium are semiconductors, and select some more semiconductors and write the energy, forbidden energy gap. That's your second question. Third one is what are the dopants used for making p-type and n-type semiconductors. Already we declared some n-type dopants, and for making p-type some dopants we discussed, and you had to write some more dopants used for making p-type and n-type semiconductors. And the last one is what is meant by normal doping and heavy doping. Just I told you the process, how the dopants will be added to the pure semiconductor to increase the conductivity so that we make n-type or p-type semiconductors. But here the normal doping means what and heavy doping means what. So like this you have to distinguish between these two processes. So you have to say in terms of how many number of dopants are required to how many number of silicon or germanium atoms. For example, normal doping means 1 part of impurity to the certain 10 power 8 atoms of germanium or silicon. So like that, you can distinguish between normal and heavy doping. Okay, so heavy doping means, what is meant by heavy doping? The dopants are to be increased compared to the normal silicon and germanium atoms. Thank you. We will meet in the next class.